Welcome and thanks very much. The purpose of this presentation is to tell you a little bit about Work Package 7, which built on earlier work in the VALUMICS project as intending to simulate using computer models a number of the food value chain case studies from the VALUMICS project. Now, although I'm presenting, this is of course joint work from a lot of people, including others at University College Dublin, members of the partners from University of Iceland, and also Assist Software, who did most of the heavy lifting on software development. So I'm going to give an overview of the modeling work we did and try to explain some of the ideas within it. And towards the end, then I'll show you the living, breathing web interface to the actual application, which is what we call a big computer program. So we'll start by looking at the conceptual framework. We'll then talk about the concept of making a model that is a hybrid of two types of simulation approach called system dynamics and agent-based modeling. We'll focus in on the decisions of the agents, because it is these decisions around things like pricing and level of production and so on that are interesting from the point of view of fairness in a food value chain, which is what we're trying to explore. We will look at one example in particular, the French wheat bread food value chain. Now, you've heard a little bit about this already in some of the presentations, particularly from Ivan for Work Package 5. We'll look at the structure of that. We will introduce some of the modeling tools that were used in developing the model. So we're starting off with a cognitive map. We'll see that, what it looks like. Then the agent behavior rule maps, and how does the hybrid approach of system dynamics and agent-based modeling work. We'll say a little bit about how we tested and verified the model, and then I'll swing over to a different window to try and show you the setup of the dashboard. So the overall framework then is, we have a problem and we focused on fairness. Our fairness, both procedural and distributional. So distributional fairness would be a measure of how a particular euro or a dollar, how is it distributed along the different actors in a value chain, which is getting a higher percentage of the value produced by the food value chain. There's also the concept of procedural fairness, which is measured by things like the learner index as a proxy, which again, Ivan mentioned previously. It's about market power and which in a pair of actors, which is able to dictate terms to some extent to the other actor. So we did qualitative and quantitative modeling and simulation, and looking at this from the perspective of socioeconomic sustainability. And why was that? Because the follow-on work package 8, is particularly interested in things like how many employees will there be in the future if the current approach continues on, or if the current approach as in structure of food value chain is actually different in the future. What will happen to level of production, number of employees, and so forth. So those were things we needed to capture in our model. So the techniques used, we'll talk about them in more detail later on, things like cognitive mapping and agent resource mapping, and agent rules definition. So we'll see more about that shortly. Then the output is a simulation model, and we call it a policy scenario simulator because it allows us to do such things as, say, alter the level of financial subsidies to see what's the effect on different actors in the food value chain if that is done. So this allows you to experiment with different policies if you're a commission policymaker, and perhaps you'll be able to see what are the outcomes of different approaches. So our overall goal then is to both experiment on and test various policy and market interventions, and so somehow give information about transition pathways, how they will develop towards more environmentally sustainable, but also socially fair food value chains. Okay, so the stages of development, and these more or less mapped onto the tasks in the work package. We started off with a conceptual specification of the model. Now, this went over and back a few times. We had to identify the information available, both qualitative and quantitative, and we had to work with expert partners within VALUMICS and in, a couple outside on the structuring and definition of the problem to make sure that we had the right background. Nothing worse than trying to solve the wrong problem. Functional specification of the problem means, the model means stating what the model will do rather than how it will do it. So again, this involves fleshing out those earlier discussions with partners using the tools we'll talk about shortly. A lot of information had to be gathered about what kind of decisions are made by actors and on what basis, because this is captured in an agent-based model. An agent is basically a computer model of an actor, whether it be a company or an individual person in a food value chain. So we had to describe the decision procedures. What are the conditions upon which an actor or agent makes its decision, and the kind of questions that the agent asks before making a decision. Later stages then are more technical, so I'll just mention that they existed. Technical specification is developing a set of computer modules and how they'll interact. It's a lower level of detail, and then all of that is converted into actual running program code or an application. And an agile approach was adopted for this, where small changes were made iteratively in quick succession. A lot of validation happened during the development of the code, but also we had help from subject matter experts in IDRI and Work Package 8 to carry out some validation of the results to see if it agreed with their what they would have expected. Okay, so an agent is our model of an actor. All models have to be simplified because you can't capture all of the possible richness of real world situation in a computer model. So you have to be selective. You have to select out what you consider are important. And that was the purpose of the earlier discussions with the subject matter experts, to identify the most important things to model. So having identified the agent decisions and behavior that were particularly interesting to us, we want to test such things as how changes in production or consumption volumes, could affect the whole of the food value chain. Could it change the structure of the chain? Would the total number of jobs be different? Would they be distributed more differently? And how would the value add distribution along the chain be modified? Would a particular actor, for example, a retailer, get a larger piece of the pie if some change was made, for example? Then Work Package 8 had developed a number of what they call scenarios, which I'm sure they'll discuss shortly. These are connected to production and financing and the kind of markets, industry-led or artisan-led markets in the French food value chain. So we considered what happens in these, and also what happens if the CAP subsidies, the public financing, maybe get changed. So our key performance indicator for fair value distribution was decided by the project as a whole, the VALUMICS project, to be the gross margin, including any public financing, together with revenues. For procedural fairness, learner index was taken as a good proxy. And the food value chain structure was assumed to remain valid until at least the year 2030, that there would be no major changes in the structure of the food value chain until that time. Now, Work Package 8 are interested in going further to 2050, when there may be changes in the structure. There may be new actors, or maybe actors disappear. But we did not have the resources to model such changes. So the example we'll look at is the French wheat to bread food value chain. There was also the Italian tomato chain modeled, but I'll just focus on this for the purpose of this talk. So what happens in this food value chain? Well, you have farmers shown in green on the left. You have cooperatives or wholesalers in yellow. There's another actor called a miller. Milling is an important process in the production of bread, where the wheat is milled to flour. Then a number of things can happen from here. It can go straight to a traditional baker, or maybe it goes to an industrial baker, who may send it on to a retailer, and maybe in-store bakers, and so forth. So we focused on the actors within the red dotted lines as being the most important for us to model. So cereal farmers, large cereal farmers, medium-sized cooperatives, medium-sized millers, and traditional bakers. So the first thing to do is identify what affects what. And this is captured in a cognitive map. Now, I'll just mention one or two things here. We're particularly interested in prices because they feed into margins, and that gives us a proxy for fairness. So for example, in the middle here, one, we have price negotiation for wheat between farmer and collector. So what are the things that would affect this price negotiation? Well, obviously the collectors themselves and the farmers. Collectors are the cooperatives or wholesalers. The average campaign price, the revenue based is based on the level of protein and a number of other different impacts. And you can see that there's many different factors being captured here. For example, exchange rates between euros and dollars, the world climate, the price of a barrel of oil has an effect on price volatility and futures, which then in turn affect reference prices for wheat. So having identified the effects, or rather, let's say the different quantities that needed to be modeled and their effects on each other, we now focus on individual agents. Now, an agent I should have, yes, somehow I missed a slide, excuse me. What is an agent? Well, the main purpose of this model was to mix together system dynamics and agent-based modeling. Now, this is a very complex system. You cannot capture all of the details in an algorithmic computer model. So what you do is you set up a number of possible collections of actors and run the model through and see what happens. You do this over and over again to see what is the average outcome. So this is called a computational simulation, when you don't have enough understanding of the internals of a real world situation to model it exactly. So you run it on a probabilistic basis over and over again and see what happens on average. There are a number of different simulation approaches available. One is called system dynamics, another is called agent-based modeling. We actually used a hybrid of the two. And the reason is system dynamics is good at looking at the big picture, a top-down view of the world, capturing flows and feedback loops in some real-world situation. Agents, on the other hand, are a bottom-up idea. An agent is our model of an actor, and it is a self-contained part of the world. It's autonomous, in other words, it makes its own decisions, but it is situated in an environment. So it has to react to what happens in the environment. And also it is social. It's interacting with other agents. So its decisions and its actions will depend on the environment and what other agents do. So it has behaviors. It senses the environments, it decides, it acts, it may have constraints on what it can do. Imagine just a real person doing their daily life and working out, what do I do in this situation, given that I only have a budget of 100 euros, what can I buy, that kind of thing. It responds to the actions of other agents. It responds to regulations from regulators, flows of goods, and so on. So it has those behaviors, but it also has goals, things that drive its behavior. Maybe it wants to optimize something like profit. Maybe it wants to maximize that, or maybe simply to satisfy certain constraints or requirements. It might have an ability to learn or adapt based on experience, and it may have stocks of resources. So for us, then, an agent is any food value chain actor. So how or what are the decisions an agent may need to make? Well, for example, down here is if buying price offer is greater than or equal to the minimum accepted selling price, then accept the maximum buying price offer among all buyers per product quality. So this is the kind of thing that our agents, and we have specific, particularly modeled aspects of agents that are relevant to fair food value chains. These are the kind of things that our agents will be checking. Are these conditions satisfied? And if it is, then they agree on a buying price per product quantity, quality, and category, and on the time of a contract. So all of these things are built into our model underneath the hood or the bonnet. So this again is perhaps a rather technical slide, so maybe I'll just very quickly go through it. A food value chain agent has attributes, things like its name, its number, its product capacity, and so on. It also has decisions or behavior rules. So what's its production? That will depend on its total capacity, its percentage utilization, production adjustment, and so on. It will have another behavior around price setting and negotiation. And all of these are going back to the cognitive map then. So here is a flow map, and it shows the impact or the effects of outside quantities or outside actions on our production. Up on the top left is an examination of the financial side. So public financing would come in, time to receive payment. The financial resources are affected by this. So there's some increase and maybe some decrease down to expenses and so on. You notice we're using the learner index and gross margin as important indicators for us. So those are the things that an agent is doing. So on the right here, we have our set of agents, our models of actors. They live inside an environment and they interact with it. Here's one agent in particular, shown as a green ball. It has its own attributes and behaviors. And one of its decisions perhaps is around its financial resources. So we've expanded that out a little bit on the left. Now, all of this is the modeling work that's done before you do any coding. Once you've done the coding and built a model, you then need to verify it, test it to make sure it's working reasonably well. Now, this image here is the local output of the Repass Symphony interface, which is not what we're using in practice. In practice, we're using a web-based interface, but this is useful for basic testing and validation. We worked with IDRI as part of this validation. So I will now, if I can, swap over to show you what the interface, the dashboard looks like. There's the website. At the moment, that is closed to members of the consortium. So I'm going to stop sharing, and then I'm going to try to share again. With a different screen. So can you see the scenario simulator?
Yes.
Okay. So these are just a couple of basic scenarios that I set up. They're copies of some other scenarios set up for validation purposes by IDRI. So if I look at one called wheat demo, and I'll just view it, the response time can be a little bit long because there's a lot of processing going on in the background with hundreds of agents and all of their individual decisions being carried out. So here are the kind of things that are relevant to the scenario as a whole. How many runs do we want to do? The more you do, the more statistically significant are your results. How many years do we want to run it for? From 2020 to 2030, that would be 10 years. That would be our decision horizon for this particular model. Do we want a percentage decrease in production volume? If so, we could adjust it on this scale, for example. When to start the decrease. Okay, because I went into view, I can't change any of these, but you can change them as you wish. Then there's a number of steps you can go through. So you can set up for the farmers, for example, different sizes of agents. So we have large and small and medium farmers. What's their cap utilization and their productivity? The cooperatives, what's their grain utilization and so on. The pay that the mill employee gets, the number of mill employees as well, and so on. Industrial bakers have their own attributes. Traditional bakers, they may get some public financing, for example. Retailers, so also consumers. So what is the consumption we expect a consumer to have? And then if we finish with this, we can, for example, run this simulation and look at the average over a period of time. So here is, for example, gross margin. So gross margin for the industry as a whole is changing a little bit over time, but we could focus in on particular ones. So I could get rid of average and total. And then if I look at this, retailers appear to be taking the largest proportion. The cooperatives seem to lose a lot and then eventually go up again. Excuse me. So there's a number of different things we can do and play with the system, and then we can export the outputs, whether to PDF or indeed to comma-separated versions of files as well. Okay, so I will pause there, and if there are any questions, I'm happy to take them during the Q&A session later on. So thanks very much for your time, and I'll try and flip back to the contact details.
This was one of the works that actually were delayed by COVID-19, and we are much later with finishing all of this than we anticipated. So nice to have this overview, the presentation on where we are at the moment.
Okay, thanks very much.